Okay, we're going to talk about hypothesis testing, and what I would recommend is on top of your Chapter 7 in your key formula sheet, I would recommend writing the word hypothesis testing because if anything has to do with a hypothesis, using a critical value test or a p-value test, you're going to want to use the formulas for Chapter 7. Just like in Chapter 6, we have Z's and T's. We use the Z when we know the standard deviation of the population. Otherwise, we're going to use the T. In either case, we have to know that either the underlying population is normal or we have to have a sample size of at least 30. If one of those conditions is not met, we can use neither Z nor T. So we're going to go about this by doing an example. We have a researcher believes the average commute for Tampa commuters is more than 25 minutes. So the first thing I'm going to write down is that the H sub O, the null hypothesis, always contains the condition of equality, which means greater than or equal to, less than or equal to, or equal to. This right here, more than, is this symbol, greater than. Because it does not include the condition of equality, that means that that claim has to be the alternative hypothesis. So I'm going to write down my alternative hypothesis, H sub A, is that the mean commute time is more than 25, and I'm going to identify that as the claim. H sub O and H sub A are always complements of each other. So if H sub A is greater than, that means H sub O has to be less than or equal to. There I have now my null hypothesis that we are going to try to reject. Okay. Another thing about this is that we only have sufficient evidence or enough evidence if we can reject our null hypothesis. Otherwise, if we don't reject that null hypothesis, we do not have sufficient evidence. We haven't gone beyond the shadow of a doubt that it's false. Okay, so now let's go ahead and draw ourselves a sketch here, okay, because we can. Okay. We're always going to put our hypothesized mean in the middle, which is 25. Okay. Now the next thing we have is that the H sub A always tells the direction of the tail. Okay, and what that means, in this case, greater than, we can see clearly that that's the direction is greater than is over here. So I'm going to draw over here my tail. But what does that mean? Well, what that means is if I get a sample, say, that's right here, that's less than or equal to, isn't it? It's less than or equal to 25. This is it's about 25. At some point, though, we're going to get so far away, so far to the right, that we're going to say, oh, wait a minute, that is certainly not less than or equal to 25. Either there's something wrong with our sample or our hypothesis was wrong. Okay, and that amount of wrongness that we're willing to be is the alpha level. That's the probability of making a type 1 error, which is probability of rejecting the null hypothesis. This is our rejection region right over here. Okay, when actually the null hypothesis was not false. Okay, so now what we're going to do in this case is we're going to be testing using p-values. The p-value has to do with the area in the tail, okay, or the area in the region that we're going to be talking about. Okay. So let's see, let's continue reading this problem. We have a right-tailed test because the alternative hypothesis has told us that. We have an alpha level. We have our mean right here in the middle, and we're going to try to figure out where our sample lies. Okay. We have a random sample of 100 commuters. So what I'm going to do as I go along is I'm going to write down all the variables that I have. So n is equal to 100. And the average time is 25.5, and that's our sample, so I'm going to use x bar equals 25.5. And as you can see, it's a little bit greater than 25, but we don't know if it's significantly greater than 25 to throw out that null hypothesis. Now it says, suppose we have a known population standard deviation of 11.5. 5 minutes. And we want to test this using p-values. Now, we know from chapter 6 that if we have a known standard deviation, we are going to be using the z-scores or the normal distribution. So we're going to go ahead and figure out then what our z-score is. Okay, z equals the mean minus the hypothesized mean over the standard deviation divided by the square root of the sample size. Okay. In this case, our sample mean, 25.5, our hypothesized mean, 25, the standard deviation, 11.5, and the sample size, 100. Now, I'm going to turn my calculator on here and pause this for just a second. You guys should also be working this out. All right, and I get approximately 0.4. Now this is a z-score. I'm going to go 2 decimal places, right? 0.4347, which is approximately 0.43. Now, what does that mean? That is the number of standard deviations I am above the mean. Now, remember, this has to do with the area. So what I want to do then is find out what is the area for something that is greater than or equal to 0.43, because remember, we have a right-tailed test. I don't know if you guys remember this, but remember back in table 4, get out table 4, what we could do is we could look up the 0.43. So on the outside, 0.4 to the nearest tenth, and 0.3, I get 0.6664. But remember, that's the area going this way. If I want to find the area to the right, I have to do 1 minus 0.6664. Alternatively, and you're going to get the same answer, we could have looked up the mirror image of the 0.43, which is the negative 0.43. Either way, we are going to get the number 0.3336. Okay, so that is our p-value. That's the area, in this case, to the right of our sample mean. Okay, because we have a right-tailed test. So now when we're comparing p-values or area, I'm going to compare that p-value to my alpha value because that has to do with the area. So we can see that 0.3336 is definitely greater than 0.05. Now, in your textbook, you're going to find that it says that when the p-value is greater than the alpha, you do not reject your null hypothesis. The reason this is because if we have a greater area greater than that alpha, that means that we are outside that rejection region, right? We're more inside, closer to the hypothesis. For that area to the right to be greater than 0.05, we have to pull back a little bit so that we can get more area to the right. So we are not going to reject our null hypothesis. Now, it's very important that we know how to write a sentence here. Okay. We want to make sure that we test the null hypothesis, but our sentence is going to be about the original claim, what was believed. Okay. So there are 4 elements we need to have in this sentence. Okay. We're going to say at the alpha equals, 0.05 level of significance. Okay, so 1 for a sentence. We're going to have the alpha level. Okay. Second thing we have is whether we do or do not have sufficient evidence. Well, here's the thing. Remember we said you only have sufficient evidence if you reject your null hypothesis. We did not reject our null hypothesis. Therefore, we do not have sufficient evidence. 2, the third thing you have to say is what you're doing to the claim. Are you going to support or reject the claim? Now, the claim can be either the null or the alternative hypothesis. In this case, our claim is the alternative hypothesis. Since we did not reject the null, that means we cannot get down to our alternative, which means we do not have enough evidence to actually go then and support the claim. And the last thing is that we have to actually restate what the claim is. That Tampa commuters travel more than 15 minutes. Okay, so you've got your alpha level, whether you have sufficient evidence, what we're doing to the claim, and what the claim was. Okay. Since I have a teeny weeny bit of space, let's go ahead and squeeze in here how we would use critical values. What would we do for a critical value test? Okay, well, the critical value test has to do with the number of standard deviations you are from the mean. Okay, we already have a z-score that we calculated of 0.43. So remember what we did last time was we converted that 0.43 into an area to compare it with alpha. What we're going to do for the critical value test is we're going to change our alpha into a z-score. Okay, that would be our z sub 0. Okay. So alpha equals 0.05. We have two choices. One, we could look up 0.05 on the inside of table 4. However, if it is a common alpha, we can also use table 5. So let's use table 5. We have a one-tail alpha, look across the top, of 0.05. And remember we said last time that what we do for the z-score is we go all the way to the bottom, and the number we see there is 1.645. Now, had this been a left-tailed test, we would have a negative 1.645. Had this been a two-tailed test, we would have had a positive and negative 1.960. Now look back on table 5. Take a second and figure out how I got that 1.960. You see how I say two-tail alpha 0.05? Read all the way down, 1.960. Again, because it's two-tailed, we're going to have a positive and a negative cutoff. Okay. Now, we have a z-score of 0.43. We can clearly see, this is our cutoff. Our cutoff is at 1.645. 0.43 is less far away than 1.645. Therefore, we also are not going to reject your null hypothesis. Okay, so you will get the same result whether you use p-value or critical value, but on your test, you need to know which is which. Again, for p-values, you're looking at the area. You compare your alpha to your z that's been converted into a p-value. For critical values, you're looking at the number of standard deviations. This time, instead, you convert your alpha into a critical z-score, and we compare it to our calculated z-score. Now, we're going to do the same exercise we just had, but we're going to say that that standard deviation, rather than being the population, was actually the sample standard deviation, which is more than likely the case, right? If you're trying to figure out something about the population, you're not going to have the population standard deviation. So this time we have S equals 11.5. Now, because we do not know the population standard deviation, we're going to use T instead of Z. Okay. So T, we're going to calculate it just the same exact way, would be 25.5 minus 25 divided by 11.5 divided by the square root of 100, and we still get the 0.43. So what's the difference? Well, the difference comes with the area when you've got your t-score. This one actually says for us to use critical values, and that's what I'm going to have you all use for t distributions, because I'm very sorry, my daughter just interrupted me. Okay, so now what we're going to do is we're going to only use, there we go, we're only going to be using critical values when we have a t distribution. Okay, so in this case, our t sub 0, oh dear, I hope it's on here. Oh, we're just going to go with 100. Okay, our t sub 0 is going to be based on our degrees of freedom. Since n is equal to 100, your degrees of freedom is 99. Now, that's not on the chart, but we're just going to go ahead and use the number for degrees of freedom 100. On your tests, I'm going to give you something where your degrees of freedom is something that is on there. Okay. So in this case, our critical value, we've got a one-tail alpha 0.05. Degrees of freedom, we're just going to use 100. Okay, because we know it's going to be somewhere between 1.660 and 1.662, probably closer to 1.660. Okay, but a little bit bigger, right? Doesn't really matter because in this case we can still see that 0.43 is definitely less than 1.660. We did not get very far away from our hypothesized mean. So again, you do not reject your null hypothesis. Okay. All right, so I think that does it for hypothesis testing. You may need some more work with p-values. You might need to do some work with writing down, there's in your textbook, something about the sentences, whether the null or the alternative is the claim, and whether you rejected or did not reject your null hypothesis. There's a little chart in your textbook. Also, there are some charts about when you reject or do not reject the null hypothesis when you have p-values and critical values. So if you need to, you can go into your textbook and write down some of those little helpers on your cheat sheet. I decided that was a little bit too brief, so let's take a look at determining sample size in Chapter 6. That's number 2. Okay. Let's say we want to estimate the mean height of American men and want to be 95% confident that our estimate is within 2 pounds of the actual mean. From previous studies, we know the population standard deviation that's supposed to be 18.4 pounds, and we want to approximate the necessary sample size. So a good idea is to always look at your question. We're looking for the sample size. Sample size is n. And on your formula sheet, we have 2 formulas for n, but this is obviously talking about the top formula because we're looking at the mean. Okay. So the formula here is n equals z sub c sigma over e squared. Okay. So this should look a little familiar, all these players. Okay, we have sigma given to us as 18.4. E, margin of error. That's the plus and minus that we're going to do. So this 2 right here is actually our margin of error. Okay. The z sub c is what we get by looking up either on Table 4 or we can use Table 5 since 95% is one of the numbers. We just use this number. We've already gone over how to find it, so I'm just going to pop it into our formula. It was 1.96. Okay, don't forget to square. So when we crunch these numbers, let's see what we get. We get about 325.153 blah, blah, blah. Okay, so we're looking at men, and we're going to sample men. We cannot sample 325.15 of them, but we want to make sure that we have that amount of accuracy, so we're just going to sample 1 more. Our sample size would then be 326 to be that level of accurate. Okay. Okay, so there's our sample size. Okay, left quite a bit of space here. We're going to need more space for the down part. Let's see what happens. On the next one, it says we want to estimate the percent of defective processors within 1% and 95% confidence. In a previous sample, we found 37 out of 577 were defective. What sample size is necessary for us to do this? Okay. First of all, we should be keyed to the fact that we've got the percent, not the mean. We also have the words 37 out of 577, so we're looking at some kind of proportion here. We should be looking at the bottom formulas for Chapter 6. And the formula here is n equals p hat q hat z sub c over e squared. Okay, so So let's see what we can figure out. Remember that p hat is your proportion, your sample proportion. We're not always going to have that. In this case, we happen to. We have that it's 37 out of 577, and when we do that division, 577, we get 0.064125, blah, blah, blah. We're going to use that p hat is approximately 0.064. Now, on MyStatLab, you might want to just leave all the decimals in there. Okay, so if p is 0.064 and q is the complement, 1 minus 0.064, that would give us 0.936. Oops, 36. Okay. Now again, I've used that 95% confidence because we're not going to worry about that number so much. Okay. What is E? E is your margin of error. In this case, we're adding and subtracting 1%, but we have to remember to change this from a percent to a decimal by moving our decimal place 2 places to the left. In this case, E would then be 0.01. Let's see what happens when we crunch these numbers. Okay. I'm getting the number 2301.272 blah blah blah. So we need to then look at 2,302 processors to be able to be that amount of accurate. Okay. Let's say though that we did not have any previous sample. Example, same as above, except p hat is unknown. We're doing this for the first time. Okay, we'd still use the same formula, right? So we're still going to have the 1.96 over 0.01 squared. But from college algebra, actually, we know that the very greatest this number can be, the p hat times q hat, the greatest product it can possibly be is 0.5 times 0.5, which gives us 0.25. So let's go ahead and put down 0.5 times 0.5, 0.25. Now let's see what we get when we don't have any prior information. I'm getting actually exactly 9,604. Now this is a case where you do not need to round up, unlike class width, right? So 9,604 processors is how many we need now. Okay. So what we can see is that just by having a little prior knowledge, wow, look what happened to our sample size necessary just by having that little bit of prior knowledge. Okay. Really don't have anything else for you other than writing on your formula sheet that if this is unknown, if p hat q hat is unknown, then we're going to use 0.25, right? And also by separating out that formula sheet for the mean and the proportion formulas. Okay, the mean formulas stop where it says minimum sample size to estimate mean, and then after that is your proportion formulas. Also at the top of chapter 6, I would put the words confidence interval. And I would write for your sample size needed, always round up. Those would be my suggestions for your formula sheet. Okay. In Chapter 6, we're going to be looking at confidence intervals. What you're doing with a confidence interval is you're using your sample to try to tell you something about your population. We start with our sample, and then we're going to add and subtract some margin of error, and then we're going to say how confident we are that our actual population parameter falls within that interval. So we have two types of confidence intervals. One is for the population mean, the other for the population proportion. I would recommend on your formula sheet separating those that are for the population mean and those that are for the population proportion. What you'll notice, for example, is that there are 3 different formulas for E. So let's start by seeing how we're going to separate out these formulas. For your population mean, like I said, you'll be starting with your X bar, and you'll be using it to then add and subtract some margin of error. And we're going to say, for example, that we're 95% confident that our population parameter, the mean, falls within that confidence interval. You'll see there are 2 formulas for the margin of error that we'd need to add and subtract to that sample mean. One has a Z sub C, and the other has a T sub C. In this textbook, if we're given the population standard deviation and either our underlying distribution is normal or our sample size is at least 30, we're going to be using the one that has the z sub c in it. If, on the other hand, we only have S, the sample standard deviation, we still have to know that our underlying distribution is normal and that our sample size, or that our sample size is at least 30. If those conditions, if not one of those conditions is not met, we cannot use anything, right? So we have either the population standard deviation or the sample standard deviation. So we need to then look at how we're going to find the z sub c and t sub c. We're going to do that in our example below, but the first step is to decide which formula to use, and it's important you pick the right formula. The other confidence interval starts with your sample proportion. It's called p hat. P hat. We're going to use this to tell us or to make an approximation for the population proportion, p. So you need to know to look for keywords like proportion or percent, this many out of that many, and it's not looking at a mean, and you want to use those bottom formulas for Chapter 6. Notice the formula is very different. We're only going to be looking at those with z sub c, and we have under this, we have the square root of p hat q hat over square root of n, remembering that p and q are complementary. In other words, q is equal to 1 minus p. Remember that from your binomial distribution. Okay. In both of these cases, we also have a formula for n. For each of them, I want you to remember to always round up. Always round up. For example, if we find that our sample size needed to be however much level of confidence with this certain margin of error is 45.2 people, we can't talk to 45.2 people, so we'd have to go ahead and survey or sample 46 people. All right, let's get down to our example now, and we'll see how these formulas get applied. We have from previous examples, we know that the heights of American women aged blah, blah, blah are normally distributed. That's important because either we have to have a normal distribution or a sample size of at least 30. And you can see down here, if you take a peek, that our sample size is actually only 5. With a population standard deviation, so we know our sigma of 2.75. We want to estimate the mean height. There's a good keyword for knowing we have to use the top formulas of this group, and here's our sample that we collect. So if we're trying to find a confidence interval for this, and I really should have had the words here, we're going to look for a confidence interval that's x bar minus e to x bar plus e. The first thing we'd have to know is x bar. Well, we could just add all those numbers together and divide by 5, but let's have a review of how you put this into your calculator. So go into your calculator, you're going to press stat, you're going to press enter on edit, and you're going to enter all these things into list 1. The next thing you're going to do is press stat. This time you're going to tab over to select calc, and then we're going to enter twice, because list 1 is the default. Okay. When you do that, you're going to get some numbers. One of them is this number, x bar equals 64.4. You also get standard deviation of both your sample and your population. But this thing doesn't know 497. That you have not put in the population, you've only put in sample. So this number right here is nonsense, right? Doesn't make any sense, even though it's given to you. We know, for example, in this example, that our standard deviation is given to us as 2.75. But we're going to do this anyway. I keep it right there because I want to show you something in a little bit. All right, so our mean is the 64.4. 64.4. We want to add and subtract some margin of error. So now let's think through again. Which formula do we use? We know it's the mean that we're talking about. We were given the population standard deviation sigma. That means we should use that formula. E equals z sub c sigma over square root of n. Okay. Well, the sigma is not difficult. It's given to us as 2.75. N is given to us, well, we've got 5 in our sample. There's 5. Okay. What we have to find out now is what is z sub c. Well, there are two ways for us to figure this out. Okay, I'm going to show you both ways because Table 5 only works in certain conditions. So I'm going to start off by using Table 4. So flip over to Table 4, please, if you've got your stuff with you. Okay, let me explain to you what's going on here. Let's say we want to be, we should estimate the mean, we want to be 95% confident, let's say. Okay, that means that we've got some margin of error. We want to be 95% confident that our actual population parameter falls in this mean somewhere. Okay, it may be that it doesn't. Maybe based on our sample, which is where we're starting, we're adding and subtracting that margin of error. Our population is outside here. That's our error out there, right? That we didn't get what we wanted. Okay, so what this means, if we've got something that's normally distributed, we're looking at the distribution of our sample means, okay? If this area in between our level of confidence is 95%, then what we have for those two tails, let's figure that out. Well, the whole thing is 100%. If we subtract 95%, we have 5% left to share between those two tails. Let's then take and divide that number in half, and then what we get is 0.025 or 2.5%. So we have 5% in this tail and 2.5% in this tail. Okay, this is the key to our Z sub C. I'm going to take up. This is the key to our Z sub C. I know I've got a lot of stuff written in there. Okay, all right. So I don't know if you remember from last time, but when we had the percentage, what we could do is we could go to our table and look up on the inside of our chart the closest we can find to 0.025 to then find the corresponding z-score in that table. So let's go. We're going to have to find it on the negative side, 0.025. I'm finding that this is negative 1.9, and that what I have up here is 0.06 to my nearest thousandths. So my Z sub C I want to use is the positive Z sub C, since we're going to be adding and subtracting. So rather than writing negative 1.96, I'm going to write positive 1.96. Now let's calculate that. When we calculate this, we get, now notice that our original data has one decimal place, so I'm going to go 2 decimal places. I'm going to write 2.4 for my margin of error, so that 2.41. 2.41 is what I'm going to be adding and subtracting, unless the directions tell you otherwise. Okay, so now we have to do our calculations. Let's see what that is. So when we add and subtract those numbers, we get 61.99 and 66.81. What we're going to say then is we are 95% confident that the average American woman aged 20 to 29 is between 60, let's just make that 62, that would make more sense, wouldn't it? And 67 inches tall. Okay, I'll be fairly flexible with this as long as you show me your calculations and some decimal clarity there. All right, so what do you want to say in this sentence? You want to say how confident you are. You want to say what it is you're talking about. You're going to list the confidence interval, and don't forget your units of measure, right? So how confident, subject, confidence interval, units of measure. Okay, now I did say that there were some other ways to do this, right? So let's look at, this is table 4. I want you guys to now turn over and look at table 5. Okay, table 5 is somewhat similar, only we have on table 5 listed up here our level of confidence right up here at the top. And you'll notice that up there you've got the 0.95. Okay, so if your confidence level is 0.95, for your Z sub C, you're going to go all the way down to where it has the infinity symbol, and that number right there will be your Z sub C. In this case, you can see it's 1.96 also. So it gives us the same result. the shortcoming of Table 5, if we wanted to be, for example, I don't know, 92% confident, we wouldn't be able to find it in Table 5. Okay. Let's say that our population standard deviation is not known. Okay. We could still do the same problem because we do know that the heights are normally distributed even though our sample size is small. But what we'd have to use for our margin of error formula would be E equals T sub C S over square root of n. Okay, so now we're going to pretend that we don't have that standard deviation of the population of 2.75. Okay. Very similarly, we know that n is 5. That's not the problem. We already have used our calculator to find S for us. Remember that our calculator may give us both numbers, but really it's only a sample that we've input. So it's 1.67 for S. Now, how do we find T sub C? Well, what you'll notice we have to use Table 5 is that we have something called degrees of freedom over here on the right-hand side. The degrees of freedom is equal to n minus 1. In this case, n is 5. N is equal to 5. So our degrees of freedom is going to be 5 minus 1, or 4. So in this case, we're going to go down to where it says the number 4 for our degrees of freedom, and we're going to read over here, this is going to be our T sub C. And let's see if we can all find it. Degrees of freedom 4. That gives us 2.776. Okay, 2.776. We have a little less accuracy with this T, so we're going to get a wider margin of error. So let's calculate this to see what we get. And I'm getting about 2.07. So that would then be the number that you're going to add and subtract from E to get your answer. So I just wanted to explain how to use that Table 5 for finding your Z sub C, which is that very last row on the very bottom, and your T sub C, where you have to use your degrees of freedom to find that value. Remember again, we're going to use the Z sub C if we know our population standard deviation. If we do not know our population standard deviation, we're going to be using S. In either of these cases, you have to know that your either your underlying population is normal or your sample size is at least 30. One more note, and that is when you're finding your population proportion, if you want to know the sample size, if we do not know P hat or Q hat, we're going to use the very largest possible number, which is 0.5 times 0.5 or 0.25. You might want to put that on your formula sheet.